Hello, everyone. We're going to now take notes on our lecture called Phase Changes. And this is our opportunity to extend what we've been doing so far about figuring out how much energy it takes to do things into a slightly larger area. So let's take a look. Okay, so we know what a change in phase is. That's when a compound goes from one phase to another. For example, when liquid water turns into steam, that's a phase change. Or when solid copper melts to liquid copper. Those are phase changes. And it takes energy to do that. It takes energy to go from a solid to a liquid or a liquid to a gas. And so um, moving from one phase to another just takes a little bit of extra energy to make that change. And what we can do in this, what we're going to learn how to do right now, is calculate how much of that energy is needed. And this is an energy diagram. Specifically for phase changes. Don't get this confused with the phase diagram that we saw earlier, where there was a section over here for solids and a section here for liquids, and this was gas down here, and that's different. That's a totally different thing. This is an energy diagram for phase changes. Let's assume this one is for water, but it could be for anything. Every compound and element, for that matter, would have an energy diagram for phase changes. We have temperature increasing on the y-axis, and we have heat being supplied here. So it doesn't try to quantify how much, specifically how much heat is here, just the fact that there's less heat being supplied here, and as you move along the x-axis, there's continually more heat being supplied to your system. All right. And so let's say we started with an ice cube, which is solid water, and let's say we started with our ice cube at -5 degrees. Hypothetically, that might be this point maybe on our curve. As we supply heat, what this graph shows us is that the temperature of our ice cube will go up until it gets to what's called the melting point. At that point, the temperature for water, the melting point is 0. So when you have added enough energy, enough heat has been supplied to get the ice cube up to 0 degrees, then something different happens. The ice cube melts. Now, we have a delta H, or an amount of energy associated with that melting. And you'll notice the important thing here. Notice the temperature is not changing when you move across this flat spot. Heat is being supplied, but no temperature change happens. And that's because this energy being supplied is used to change the phase from solid to liquid. And then after you've supplied enough heat, you get to a point where all of the ice has turned to water, to liquid water, and then the temperature starts going up again as you continue to supply more heat. And then you get up to 100 degrees, which for water is its boiling point. And again, we've got one of these plateaus where there is a flat spot on the graph, and there's another delta H associated with this section where we're changing liquid water at 100 degrees into steam at 100 degrees, or vapor. And then you've got your water vapor increasing its temperature beyond that. All right, so that's how this figure works. So the important piece was this temperature doesn't change on the plateaus, but we're still supplying heat. That heat being supplied on the plateau, let me see if I can go back easily, not easily. The heat being supplied here, again, remember, is being used to change the phase, not to change the temperature. The heat being supplied in this section is changing its temperature, as you can see, because the temperature is going up by the slope of this line. When this line is flat, the temperature is not changing, but heat is still being supplied. That heat is being used to change the phase. All right? So, and what's actually happening on those plateaus is there are intermolecular forces between the molecules of the compound that hold it in a given phase. And you have to supply enough energy to break those intermolecular forces to move from the solid to the liquid, or the liquid to the gas phase. So that's what is happening on the plateau part of the figure. Okay, so now there are 4 different types of energy phase changes that we're going to consider. And they're all laid out here, so we'll walk through them one by one. They have kind of complicated names, but they're simple concepts. This thing called the molar heat of fusion. First of all, this term molar always means per mole. So, in other words, the heat of fusion for a single mole of the compound. So, the molar heat of fusion is the heat absorbed by 1 mole of any substance when it melts from solid to a liquid. Now, I'm not sure why we call it heat of fusion when we're turning a solid into a liquid, but there it is. The abbreviation for this is delta H FUS. See this little FUS down here? That stands for fusion. This is the amount of heat required to melt 1 mole of a substance. And of course, water is going to have a different molar heat of fusion than ammonium chloride is going to have, which will be different from elemental aluminum, whatever. Each compound or element will have its own molar heat of fusion. The reverse of that process is called the molar heat of solidification. That's the heat lost when 1 mole of a liquid solidifies. And we abbreviate that delta H solid for solidification. All right. Now let's take a look at the next one, the molar heat of vaporization. By now you're probably seeing the pattern in these names. The molar heat of vaporization is the amount of heat required to vaporize or turn the liquid into a gas 1 mole of a substance. And we abbreviate that with delta H VAP. And then finally, the reverse of that one, the molar heat of condensation. That's the heat lost when 1 mole of a vapor condenses. So you've got, this is the gas to liquid, this is the liquid to gas, this is the liquid to solid, and this is the solid to liquid phase changes. All right. So here are some of the actual numbers. For the examples I'm giving you are for water. Again, each compound or element is going to have its own numbers for this. The delta H of fusion, that is the amount of heat needed to melt 1 mole of, in this case, water from solid to liquid, is 6.01 kilojoules per mole. You have to add this much heat to melt 1 mole of ice to water. And then the reverse process, the delta H of solidification for water, is the same number but just different in sign, which probably makes sense if you think about it. If it takes 6.01 kilojoules per mole to melt water, you should have to remove 6.01 kilojoules per mole to solidify water. All right, so these numbers are the same numerically but opposite in sign. And that's what this says. The enthalpies, these numbers, the delta H's, are opposite in charge. So when water changes from a solid to a liquid, it has to absorb heat. And again, by our convention, when we're talking about thermochemistry, if your system is absorbing heat, we show that as a positive value. When water changes from a liquid to a solid, it has to lose heat, and so your system is giving off heat. That means we show it as a negative value. You have to be given these numbers. You're not going to have to calculate them. These are excellent candidates for a note card, but in general, I think I would probably put these on the test. I don't want you to hold me to that. These are constants. These are not things that you would have to, in general, memorize. You would look them up one way or another. Let's do an example, because I love examples. How much heat is needed to change 28 grams of water at 0 degrees to liquid water? So water, what I'm saying here, water at 0 degrees, that's basically ice. So how can we change water, 28 grams of ice into 28 grams of liquid water? And I'm giving you the delta H of fusion because that's the constant that we need, as 6.01 kilojoules per mole. All right, so the calculation is fairly straightforward. We take 28 grams and we convert our grams to moles because you'll notice that the delta H of fusion is given per mole, so we can't use grams. We've got to go to moles. And then we simply multiply by the molar heat of fusion, 6.01 kilojoules per mole, to find 9.35. So in order to take an ice cube at 0 degrees and turn it into a puddle of water at 0 degrees, you have to give it 9.35 kilojoules for that 28 gram sample. All right? Here's a more complicated and interesting example. How much heat is needed to change 200 grams of water from 85 degrees, so it's liquid water at 85 degrees, to 100 degrees, liquid water, and then change that liquid water into steam? Aha, a more interesting question. So here is the specific heat of water. Remember that from our current labs. 4.184 joules per gram degree C. That's the specific heat of water. And then you also need to know the delta H of vaporization, which is 40.7 kilojoules per mole. Let's see how this works out. We need two calculations, and I'll show you why. Let's take a quick look at slide 3. We're going to be starting out with water at around 80, I think it's at 85 degrees, which is maybe about here on our graph. We need to figure out, so the whole problem takes our water from 85 degrees to 100 degrees as liquid, and then change that liquid water into a vapor. So we have to do two calculations, one that corresponds to this part of the change, and then another one that corresponds to this part of the change. All right? This part of the change, this first part of the calculation, is one that we've done many times before, where you've got a temperature change and you use the specific heat of a compound to figure out how much energy you have to add. So let's go back. So like I said, first we're going to calculate how much heat is needed to change the temperature from 85 to 100 degrees. We've got liquid water. It's going from 85 to 100, so let's see how that looks on here. We use Q equals Cm delta T because we've got a temperature change, and not a phase change, and so we use Q equals Cm delta T. So Q equals the mass, the specific heat of water, and the temperature change, 85 to 100. You do that calculation and you get 12,552 joules, or round to 12,600 joules, or 12.6 kilojoules. So we needed 12.6 kilojoules of energy to raise the temperature of 200 grams of water from 85 degrees to 100 degrees. That corresponds to this part of the change from about here. Let's say that's about where 85 is. 85 up to 100. So at the end of that calculation, we've taken our water from 85 degrees up to 100 degrees, but it's still liquid water. The second part of the calculation will take this liquid water at 100 and change it into steam at 100. Whoops, sorry, I went to the wrong slide. All right, so let's do that second part. I don't know why these slides did that. Let's do the second part. There we go. Now we're going to calculate the amount of heat that's needed to convert the water from liquid to gas. This is where we use our delta H of vaporization. There's no temperature change here, so it's not a Q equals Cm delta T question. It's a vapor change calculation. Sorry, it's a phase change calculation. We have 200 grams of water. We got to convert the grams to moles, and then because delta H of vaporization is given in kilojoules per mole, and so we use the molar mass of water to convert 200 grams into moles, and then we multiply by the delta H of vaporization, 40.7 kilojoules per mole. And if you do that calculation, you get 452 kilojoules. And then we add those two numbers together. We have our 452 from this calculation and our 12.6 from the previous calculation, and you get 465 kilojoules. That's how much energy it takes to raise water from 85 degrees as a liquid to 100 degrees as a vapor. Two-step calculation. All right. Now you can put this together and have a very long calculation where, for example, you start with an ice cube at minus 10 degrees and you have to change that into vapor at 110 degrees, and there are many, you can imagine there are many steps in that kind of process, but it's always a stepwise process. It's the same basic idea each time. So we're going to do lots of practices with these, don't worry, and I'll work through some examples on the board first. But now you have the basic tools you need to do phase change calculations. Very good. There's our energy diagram one more time. You'll become very familiar with these. All right, that's it for now. Thanks.